it's already night, but maybe Europe are still noon or something. Anyway, hello everyone. And shall we start the first session of the third day? First speaker of this session is Professor Andrei Barvinsky. He's going to tell us about Lorentz non-invariance as a palladium of locality, unitarity, and renormalizability in quantum gravity. Andrei, please start.
Okay. Well, first of all, let me thank the organizers for a nice workshop. Actually, I would say that I never attended before the meeting with such an intensity of discussions and efficiency of this discussion. So I'd like to thank the organizers for creating this productive atmosphere. Now, the subject I will be talking is actually related to what we discussed on the first day of the workshop, and this is the problem of ghosts, which, as I understand, the general opinion is very diverse on the role and fate of ghosts in quantum field theory and quantum gravity. But I will actually adopt, I would say, a widespread view that the absence of ghosts should be really a criterion of, just a moment, let me again. The absence of ghosts should be a criterion of construction of a consistent and healthy theory. And if this theory also possesses such properties as locality, renormalizability, and consistency in ultraviolet domain, then we can hope that this theory can be a good candidate for the description of our nature. So I will talk about the mechanism which provides a combination of all these properties, and in particular there will be the discussion of two models which both seem to provide some of these properties, and the first part of the talk is basically field theoretical, and I will basically show that Horava gravity with the property of Lorentz, violation of Lorentz, Lorentz invariance, will provide the renormalizability and a consistency in the high energy domain, at least for low dimensions. Then the second part of the talk is perhaps more interesting for cosmologists because of these applications and motivations. But this is a model which also shares a number of interesting properties, including the eradication of ghosts, the existence of the unitarity domain, which are rather similar to Horava gravity. And in the end of my talk, I will try actually to combine these models and see whether the second model can be considered just as an effective field theory, or maybe it can be unified with Horava gravity regarding its renormalizability properties. So let me now go to the first part of my talk, and here I would I don't think that it is worth discussing again and explaining again one conventional Einstein general relativity is not renormalizable. And of course, this is because you have the derivatives in the vertices, second order derivatives in the vertices. You have dimensional full coupling constant, And to avoid, to circumvent the difficulties of non-renormalizability theory, one can introduce higher curvature terms in the action, and the theory will be renormalizable. And as it was shown some years ago, it is actually asymptotically free, at least modulo some subtleties regarding different sectors of the theory. But the problem is that this theory is not unitary, simply because of the presence of high order derivatives. It has ghost poles, and it leads to all this confusion associated either with negative energies or with negative norm states in the Hilbert space, negative residues, the poles of the propagator, and so on. So the remedy against this difficulty can be the following. We can introduce, as it was done by Horava more than 10 years ago now, we can introduce high order derivatives, but only in the spatial, with respect to spatial coordinates, while leaving the second order time derivatives in the Lagrangian of this theory. And then in the assumption that the theory has additional global symmetry with respect to anisotropic scalings of coordinates, then Horava suggested that this theory can be actually renormalizable within the class of theories with finite set of counter terms. Of course, Lorentz invariance in this case is violated, and but instead of this, we have to, in order to be constructive, we have to, of course, retain certain local symmetries in order to be able to distinguish between, to have a criterion of selection of proper counter terms in the theory. And as such a local symmetry, this usually what is considered is the theory of corresponding to diffeomorphisms which preserve the foliation of space-time by three-dimensional hypersurfaces. So in the ADM parameterization of gravity theory with the conventional set of Arnovitz-Deser-Misner variables, one can introduce the corresponding anisotropic scaling transformations and scaling dimensions of these variables, which are shown here. I believe you see my mouse, yeah? Then, and with this choice of anisotropic scaling dimensions, it is not too difficult to understand that the set of the structure of the bare Lagrangian in the theory of classical Lagrangian, which might lead to renormalizability, is the one that is shown on this slide. So it has a standard typical for Einstein general relativity kinetic term, which is at maximum quadratic in time derivatives of metric coefficients. And it involves a rather non-trivial potential term, which is built of the chain of the monomials in the curvature up to some finite order in derivatives. And the order of these monomials for the theory to be renormalizable simply just by power counting arguments can be finite. So what is important? It is important that we are increasing only the, in the inverse propagator of this theory, we are increasing only the power of spatial derivatives, while the second time derivatives are still the second order. And this means that the propagators have a typical poles not leading to negative residues and ghost states. Now, in what follows, we will basically consider the so-called projectable theory, which is projectable Horava gravity theory, which is characterized by freezing the value of the lapse function. Well, why it is so, I will describe later. Well, just to give it ahead of time, I would only say that the proof of renormalizability of this theory in any dimension will be more or less rigorously shown and demonstrated only for projectable models. Non-projectable models thus far are not shown to be renormalizable. Now, but of course, there is a lot of much more versions and when the lapse function is not frozen, and then in this case, the number of tensor structures in the action is of course much more complicated. But anyway, let us stay within this set of structures and just give some simple arguments in favor of renormalizability of this theory. The main point here is the following, that in the theories like this, the counting of the degree of divergence of Feynman graph is different from the counting in the usual Lorentz invariant series. This is because the replacement of the typical momentum integral in Feynman graphs like this, where you have instead of p squared, Lorentz invariance p squared, you have the sum of the square of the zeros component of the momentum vector and some power z of the square of the spatial momentum. Then the physical, then the degree of divergence of this diagram is actually determined not by the physical dimensionality of this quantity, but by the scaling dimensionality. And then it is easy to show that the for a given dimensionality of space, which is denoted by d here, the value of critical value of z, of the parameter z, which determines the power of spatial derivatives in the inverse propagator of the theory, or the power of the corresponding curvature structure in the potential term of the Horava-Lagrangian, then this critical value above which this theory becomes renormalizable is given by a simple relation z equals d, which means that in the case of say 2 plus 1 dimensional Horava gravity, the potential term is rather simple. In the case of 3 plus 1 dimensional theory, the potential term should involve not only the squares of the 3-dimensional curvature, but also cubic structures, which is the set of which is rather long, and I will not at them thus far at the moment dwell on this. So the situation, however, is not so simple, because the power counting argument in favor of renormalizability of such kind of theories is not enough. And the explanation why it is not enough is very simple. In the transition from the Lorentz invariant theory to the theory of Horava gravity, Horava-Lifshitz type, what happens? The denominators get replaced by the structures which are shown here, so that the sum of square of the corresponding loop momenta of the zeros component of the loop momenta, some high plus some high order power of the spatial momentum, and the coefficients in front of this combinations a, m, and b, m, they are not fixed, unlike in Lorentz invariant theory. And moreover, the signs and the values of these coefficients actually depend on gauge fixing, strongly depend on gauge fixing. And in order to provide the validity of the BPHZ renormalization procedure, R operation, subtraction of side divergences, one should provide the following property. This can be rather rigorously shown, that both coefficients in all the propagators of the theory, they should be either both positive or both negative. And this fact actually depends on the gauge fixing. because depending on the choice of gauge, you can operate with different values of A and B in this expression. And the main, it was a kind of a challenge actually to find a set of gauge conditions which really allow one to provide the positivity of both coefficients. So these gauge conditions, they are actually shown here. This is a kind of a generalization of the relativistic gauge conditions in the Lorentzian version of this theory, Lorentz invariant version of the theory, to the version in which you have the Horava prescription for the Lagrangian. So this section, the choice of these gauge conditions is shown here. It is characterized by the presence of the time derivative of the shift functions plus spatial derivatives of the spatial metric coefficients, spatial derivatives, Laplacians, and spatial gradients to some power, and also the gauge fixing matrix, which is in the gauge fixing term of the Lagrangian. And the major conclusion that we came to by analyzing the choice of these gauge conditions, it is that this projectable Horava gravity model that can be renormalizable in any dimension due to this additional difficulty that arises in Horava gravity models. For non-projectable theories, the situation is much more complicated, and at the moment, simply we do not have any type of conditions sufficient for renormalizability of the theory. Now, there is another issue, very important issue here. This is the issue of gauge invariance of counter terms. In a sense, gauge invariance of counter terms, this is the only selection criterion for selecting the needed structures which provide renormalization of divergent terms. And it turns out that the usual conclusions about gauge invariance of these counter terms is in principle turn out to be under a question sign in the series of this type due to violation of Lorentz invariance. And here I can give a very long list of pioneering names of pioneering people pioneering in this field. So in order to extend these old results on the BRST structure of renormalization in the series, we had to actually start the analysis of this problem, I would say, from scratch. And the results of this analysis are as follows. In a sense, in order to guarantee the covariance of counter terms under the gauge transformations of in the theory, of a rather general type. I don't have time now actually to explain the details of this procedure, but the construction, the extension of the ground field, the ground covariant formalism for establishing the BRST structure renormalization, which can be based on the following two facts. First of all, this is a choice of background covariant gauges. Then this is background field extension of the BRST operator plus inclusion of functional sources, the generating function of the theory, into the so-called gauge fermion. So if one takes the combination of these methods, then one can prove the following things, that BRST structure of renormalization takes place via the so-called decoupling of the background field. And in this procedure, there is no need actually even to consider the power counting or use the field dimensionalities of the underlying operators. And in this way, one can extend the Lorentz symmetry to Lorentz, to extend the usual conclusions on the covariance of counterterms to Lorentz symmetry violating theories. And moreover, it can actually, this statement of renormalization can even be extended to non-renormalizable series or even effective field series. Well, I don't have time really to explain how the details of this derivation. Uh, the main statement here is the following: that we have to extend the BRS operator, the nilpotent BRS operator in the BRST construction of gauge theory by additional terms. We also have to include the sources of the generating functional into the extended version of the gauge fermion, and then replace the functional integral representation for the generating functional in the form which is shown here. So you have, instead of the usual original structure, classical action plus BRST exact term of this form, you have a similar construction, but with the extended definition of a nilpotent BRST operator and the extended fermion. This path integral will satisfy a typical gauge independence condition on shell. And this is a very important property actually in a gauge series, which is missing in a presently very popular approach of asymptotic safety quantum gravity theory, because it is well known that the vectoric equation underlying this construction, unfortunately, in this equation, the similar property is missing. It is impossible to perform introduce the filtering function in the vectoric equation in such a way that the resulting effective action will be both gauge invariant and gauge independent on shell. But here the situation is typical, and it actually exactly corresponds to the original ideas of Weinberg regarding essential coupling constants, that this functional or effective action, they are both on shell, they are gauge independent. Therefore, one can formulate the notion of essential coupling constants, which are gauge independent. And the structure of the renormalization actually, so to say, decouples into the independent renormalization of the classical action with the very well known and understood set of invariant counter terms in terms of the original gauge field, plus rather complicated renormalization of the gauge fermion sitting in this path integral. And the structure of the renormalization of this this fermion is actually rather irrelevant. What is physically important and actually corresponds to physical properties of the renormalization group flows. This is just renormalization of the original classical action in terms of the original gauge field. And in this way, we were able to apply all this wisdom to the analysis of asymptotic freedom in 2 plus 1 dimensional Horava gravity. For example, in this case, there are only 3 coupling constants in the Lagrangian. There is only one physical mode in the physical sector of the model. This is a scalar mode. There is on-shell extension, as is known, is not unique, and it is defined up to the addition of the quantity of the term proportional to equations of motion. And exploiting this ambiguity, one can show that there are 2 essential coupling constants. This is lambda and the ratio of G of the Newton coupling constant to the square root of the coefficient in front of the curvature scalar squared term. And by using the background covariant gauge fixing conditions and the corresponding gauge fixing term like they're shown here, one can derive beta functions for these essential coupling constants which are presented here. And there is a very powerful check on the validity of these results, because this beta function, they should not depend on the choice of gauge condition, in particular on the choice of these parameters which enter here, which are free parameters in the gauge fixing procedure, or even more complicated situation when you perform the calculation of this beta function in the conceptually different set of gauge conditions, saying conformal gauge. It is interesting that if you calculate these beta functions in conformal gauge and the regular relativistic gauge that was just introduced above, one can see that the beta functions for non-essential coupling constants is indeed they are indeed different. But if you go over to the beta function of essential coupling constant G, for example, then it is just one and the same. So here is a picture of renormalization group flow in this parameter theory with two essential couplings. And this picture shows that in the two-dimensional place of lambda and G, there is first of all there is a non-unitarity domain belonging to this set range of values of lambda. If you remember, lambda is a coefficient in the kinetic term of the Horava gravity. And there is asymptotically free UV fixed point here. There is also another fixed point here at the very boundary of the unitarity domain. I don't think that I have time to discuss the properties of this renormalization group flows. Let me just say that what we have now, we are actually heading towards renormalization group flows in 3+1 dimensional Horava gravity, which is fantastically complicated, calculationally fantastically complicated problem. But at the moment, we already have beta functions for two coupling constants. Altogether, there are 7 coupling constants here. 6 of them are essential. And for 2 of them, for G and for lambda, the final results are already given. And these results actually show that the picture, for example, in the two-dimensional plane of variables of lambda and the variable alpha, which is some particular combination of the coupling constants mu1, mu2, etc., mu5, in the cubic in the curvature term of the Lagrangian, then the behavior in this two-dimensional plane is very interesting. One can show that the beta function, actually a beta lambda function, actually goes to 0 at this curve, and this curve, here it is negative, positive, and vice versa here. And potentially one should anticipate the origin of asymptotic freedom in all other coupling constants in the corresponding six-dimensional surface, which would equal this one-dimensional line in the direction of other coupling constants. So there is a hope that this theory also will have some interesting free, or in the sense of asymptotic safety. So basically, that's the end of the first part of my talk. At the second part of my talk, how much time do I have, by the way? Can I?
Still almost 2 or 3 minutes.
2 or 3 minutes. Okay.
Yes.
Maybe I will try to finish in 5 minutes if
Yes.
you allow me, please.
Yeah.
Definitely, it's not enough really to show the details of the second model, which is of course it's very different from the class of Horava gravity models, and I would say that this part of my talk may be more interesting for cosmologists. And actually here we are moving from the UV domain to, so to say, to infrared domain of this theory. But this theory, what does it share in common with the class of Horava projectable Horava gravity models is the following: that it also suffers from or benefits from violation of Lorentz symmetry and diffeomorphism, local diffeomorphism symmetry. It is has the property of fixing the lapse function. It's just like in projectable Horava-Lifshitz model. and the same number of degrees of freedom. And it is interesting that this model, which we call generalized unimodular gravity, actually this is the theory which arises from Einstein gravity by imposing such a constraint between the Lipschitz function, of the theory and the function of three-dimensional metric coefficients, which is just the determinant of gamma ij. And this is a generalization of a very well-known unimodular gravity theory. The advantage of such a constraint is the following, that it actually generates effective stress tensor of effective matter composed entirely of metric coefficients. And this effective stress tensor on the right-hand side of Einstein equation, it has a form of the perfect fluid one. And it has a barotropic parameter W, which actually given by the logarithmic derivative of this function n of gamma, which is just a function, rather generic function, which parameterizes the set of such theories. The motivation for the introduction of such a theory was actually generating the dark energy, because it is well known that the effective state and equation of state of dark energy, this is a varying value of the barotropic parameter W. There was a hope that this can be generated by such a type of modification. Well, the construction of the canonical formalism in this theory shows that there is the whole plethora of constraints, starting from trivial primary constraints to the quaternary constraints. And at the level of quaternary constraints, there is a bifurcation between the phases of this theory. And one of these branches of this theory is just a typical usual general relativistic branch, with the vanishing value of the Hamiltonian constraint. But there is also the so-called GUMG, generalized unimodular gravity branch, which possesses 3 local degrees of freedom, tensor and scalar gravities. And question arises whether this theory is really stable, non-ghost. And the answer to this question depends on which particular background you're considering this theory. And this theory, interesting branch of this theory is this GUMG branch. It actually corresponds, it does not include flat space. And it is interesting in cosmological applications. It is easy to show that in this branch, the theory on the Friedman-Robertson-Walker background can be described as usual by the Friedman equation with the so to say dark fluid source on the right hand side, and this dark fluid can be expressed in terms of the coupling, in terms of the integration constants of equations of motion, and it devolves as according to this rule, and depending on the choice of n as a function of gamma, this theory can imitate either dark energy, or it can also imitate inflation stage. And there is a one can reconstruct from the main features of inflationary scenario. One can reconstruct the dependence of the function n of the on the metric coefficient, which is shown here. And this dependence is rather peculiar. For example, it has, so to say, non-analytic term, the ratio, the power of the determinant of three-dimensional metric, fractional power. And this fractional power, as we will see later, it is actually directly related to the parameters of the CND power spectra, primordial power spectra of Rayleigh radiation generated during inflationary scenario. In order to get this power spectrum and to compare the results with the necessities of the observational cosmology, one can develop GUMG, cosmological perturbation theory, And what is interesting that in this perturbation theory, the role of inflaton is actually played by the scalar graviton in the physical sector of the model. And when this, it is interesting that this mode, it has a non-trivial unitarity domain. So it is not a ghost one, provided you have a very stringent restrictions on the parameters, functional parameters of this model. For example, this combination should be positive, which provides the non-ghost nature of this mode, so that this mode can be normalized canonically, normalized to unity, its kinetical term. And there is also a condition of absence of tachyons or gradient instabilities, which enters the construction of the corresponding speed of sound of excitons of the excitations of this variable. Well, it's not very hard to actually to apply this in the domain of unitarity of this theory. It's not hard to apply it for the calculation of inflation spectra, and the result is rather interesting. On the background, which was shown above, which corresponds to inflationary evolution, the parameters of the inflationary spectrum is such that its the most interesting parameter, this is just a spectral tilt of the spectrum. It is related to this fractional power in this ansatz for the function n of gamma. And there is one additional interesting property, which looks as follows. One can calculate the ratio of the tensor to scalar signal in the CMB spectrum. And it is interesting that this ratio, it is composed of two quantities. First of all, this is the exponentially high e-folding number of the during the expansion inflationary expansion stage, and the parameter of spectral tilt difference of ns from 1. It is interesting that the theory demonstrates a kind of naturalness in the which is um, uh, um, you see in the inflationary theory there is one exponentially big parameter. This is a kind of a sacred cow in this science, which is e to the power 60 e-folds, which separate the point of horizon crossing, the first horizon crossing point of formation of the observable, presently observable CMB spectrum till the moment of the end of inflation. It is interesting that the parameter R, the ratio of the tensor to scalar signals, they are given by such an interesting combination, e to the power minus n, which is fantastically small number, but when it is raised to a very small number like this, it gives the magnitude which is very close to what is observed, what is anticipated to be observed. So there is an upper bound on this ratio, which was the tensor signal has not yet been observed at the present level of the precision cosmology. And it is interesting that without introducing any other exponentially big numbers, there is only one number, which is O1 quantity in this parameterization of the Lagrangian the generalized unimodular gravity model.
Andrei, sorry, please summarize your talk.
Okay. Let me summarize. Basically, I just wanted also to give the picture of covariantization of this model, which consists in the introduction of Stueckelberg fields. And it is interesting that this covariantization, it leaves the representation of this model in the form of the K-essence, of a very interesting type, so that one of the Stueckelberg fields played the role of the scalar field of this K-essence model or K-inflation model. In particular, this explains the nature of the expression of a very particular expression for the speed of sound of the excitations of this K-essence field. Well, I don't think that I have time for reconstruction of this decoupling of spatial Stueckelberg fields and reconstruction of this hydrodynamical, so to say, representation, an equivalent of this model. But it is interesting that this reconstruction actually shows the following thing, that the Lagrangian of this model in covariantized version, it actually starts with the action of the so-called cuscuton model, which does not have, as is well known, no degrees of freedom at all. And the physical degree of freedom of this system, which is a dynamical K in Platon, is actually sitting in the corrections to this expression. And these corrections, they have the structure of slowly varying logarithmic corrections, very characteristic of the effective field theory. So it is quite possible to imagine that this model, generalized unimodular gravity, which is free from ghosts and can actually describe the inflationary stage, it is just effective field theory of some more fundamental construction. Well, there is still a hope that Bung theory and Horava-Lifshitz theory, they can be unified. Well, I don't have time really to talk about this. This unification is rather interesting, and there is some indication that it is possible to really render this unified theory renormalizable within the so-called generalized renormalization group, which has a form of the functional renormalization. But this is something very different from what is usually understood now in the framework of asymptotic safety approach to quantum gravity. Well, I don't have time to get into more details of this, what I said before, but basically let me finish with conclusions that are listed here. So this is basically the conclusion of renormalizability of projectable class of projectable Horava-Lifshitz gravity models, and some connection with the generalized unimodular gravity model, which shares a lot of similar properties and maybe actually connected to the renormalizable Horava gravity at a deeper more fundamental level. Thank you very much.
Thank you, Andrei, for a nice talk. Now session is open for question, but first, Anupam and Robert asked the question in chat. So Anupam, please directly ask Andrei.
Thanks, Andrei. It's a wonderful talks. It's very nice. Just a curious question that what happens to the singularity problem, and especially what happens to the BKL kind of instability? Has someone looked into these kind of issues here?
I don't think that I can say something interesting in this. You see, point is that singularity theory. So you see, it depends on your. You see, this model. It does not exist, or it is not really interesting in context of asymptotically flat space-time. And the singularity problem is most interesting in context of black hole physics, and in context of some clustering of matter and of black hole type singularities. If you talk about, if you would like to talk about the singularity of the cosmological nature, say the singularity that could have preceded, say, inflationary stage, then I believe that one should consider absolutely different approach. I don't know. In a sense, nothing has been done with this model in the asymptotically flat context. You see, this theory has two branches, and the asymptotically flat branch is, so to say, trivial. It is simply because the variable which is responsible for the this dark energy fluid. This is some global variable which actually curves the whole of spatial space-time section, and it does not allow flat, asymptotically flat solutions. So basically, this is the I don't know whether you are satisfied with this answer, but basically this is the status of this model at the moment.
No, I just wanted to know. I was just curious. Nothing about that. Thanks.
Okay, Robert, please ask question.
So I was wondering, in the inflationary model which you presented, how does reheating proceed?
You mean what was the criteria?
How is the transfer of energy into standard model particles at the end of the inflationary phase?
Well, you see, this is the mechanism is the following. Since the presentation was rather hectic, I would say. So you see, this is the functional dependence of this lapse function on three-dimensional metric coefficients. And as you see, the beginning of the inflationary stage here is described that corresponds to very small values of gamma. This is gamma. This is A cube. This is just a volume of the expanding universe. And gamma star. This is the volume of the universe at the end of inflation. So in this model, so to say, the transition from the state of W close to -1 corresponding to inflation, this is just input into the Lagrangian, so to say. This is the way how this exit from inflation. And of course, on top of this inflationary background, the physics of the of other matter ingredients, this physics is more or less equivalent to what is going on in the conventional inflationary scenarios with the inflaton, with the scalar inflaton in chaotic inflation or something like this.
Okay, maybe we can talk about it later. I don't understand the answer, actually.
Okay, yeah, please discuss later. And sorry, Philip Sravan, Richard, Nikolai, maybe please ask your question in the discussion session because time is over. So yeah, so let's thank Andrei again.
Okay, thank you.